Assalamualaikum, my name is Nur Amani binti Muhammad Amin. Today we want to present about this project. This project focuses on designing a sustainable water supply and wastewater management system for a kampung orang asli community in Malaysia. Currently, the village rely on untreated river water for their daily needs, which increase the risk of waterborne disease and poor sanitation. Therefore, this project aims to provide a safe and reliable water treatment system while considering the challenges of a rural environment, such as limited electricity and remote access. Using environmental engineering principles, we design suitable water and wastewater treatment system that support public health, environmental protection, and sustainable development goal 6, which is clean water sanitation.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Amani binti Ismail and my metric number is 2022664548. So for the program segment is kampung orang asli community faces several critical engineering and environmental challenges. First, untreated water source and health risk. Around 500 residents rely entirely on raw, untreated river water for drinking and cooking. This exposes them to dangerous waterborne diseases like cholera and typhoid due to pathogens and high turbidity, especially during heavy rain. Second, poor wastewater management. The village lacks a proper sewage system, meaning domestic wastewater is discharged directly back into the river. This creates a dangerous pollution loop since the same river is used as their primary water source. Next, remote location and power constraints. Being in a remote forest area, the village has a highly limited electricity supply. Energy-intensive or overly complex commercial treatment technologies are not practical here. So last, regulatory compliance. The current situation fails to meet Malaysian standards, including the MOH Drinking Water Quality Standard and the Environmental Quality Sewage Regulation 2009.
Next, water demand analysis is the first step in designing a water supply system. It determines the required treatment plant capacity and ensure that the system can provide sufficient clean water during both normal and peak demand periods. The design is based on a community of 500 residents living in 100 houses. Each person is assumed to use 180 liters of water per day, and approximately 80% of the supply water becomes wastewater. The average daily water demand is calculated by multiplying the population by the per capita water demand. The community requires approximately 90 cubic meters of water every day. To account for a period of high water consumption, such as festival or hot weather, a peak day factor of 1.5 is used. Therefore, the treatment plant should be designed to supply up to 135 cubic meters per day. The peak hour demand represents the highest water consumption within a single hour. This value is important for sizing pump, pipeline, and storage tank. Not all supplied water become wastewater because some water is used for cooking, evaporation, and other losses. Based on the design assumption, 80% of the water. Based on the calculation, the community requires a relatively small-scale water treatment system. The water treatment plant is designed to treat up to 135 cubic meters per day to ensure reliability during peak demand, while the sewage treatment plant is designed for a wastewater flow of 72 cubic meters per day. The proper system is practical, economical, and suitable for rural communities with limited infrastructure.
I'm Nur Afina binti Muhammad Sani, and I'm presenting our decentralized wastewater treatment system, or DWATS design. Standard mechanized treatment solutions like activate sludge system that rely on heavy energy and complex blowers are simply not practical or viable for off-grid or remote areas. Crucially, our discharge site is directly upstream from the Kampung Orang Asli community who rely heavily on this river for their daily domestic and drinking water needs. To protect public health and downstream ecosystem, this system is engineered strictly to meet DOE Standard A requirements. That means our final treated effluent must not exceed 20 mg per liter of BOD and 50 mg per liter of suspended solids. Thirdly, secondary treatment. Finally, the effluent reaches a horizontal subsurface flow constructed wetland spanning 1,438.1 meter square. Using a 0.6 meter gravel metric, it biologically degrades use of organic pollutants. Thirdly, for public health and safety, by keeping the water line below the gravel layer in the wetland, we completely eliminate unpleasant odors and prevent mosquito breeding vectors near the village. And lastly, for SDG integration, this design directly advances SDG 6, which is clean water and sanitation, by bringing safe sanitation to an indigenous community, and SDG 14, which is life below water, is by preventing eutrophication in the local river system. For overall performance and sustainability benefits of this design, firstly, regulatory compliance and performance. As shown in the graph, raw effluent with a BOD of 147.4 mg per liter is reduced to below 20 mg per liter at the wetland outlet, well within the DOE standard A limit. Total suspended solids are similarly controlled to below than 40 mg per liter. Secondly, zero energy and low maintenance. Because it uses zero electricity, power blackouts in rural areas won't cause system failures. Furthermore, the in-house tank stabilizes sludge over long periods, requiring discharging only once every 2 to 3 years. To ensure long-term practical viability, our DWATS operates 100% on gravity flow using 0.0 kilowatt of electricity. The system processes an average effluent flow rate of 72 meter per day through 3 main zones. Firstly, preliminary treatment. The water first enters an inclined bar screen chamber with a 0.25 meter channel width and 25 mm bar spacing. This manually clean screen captures coarse debris to protect downpipe hydraulics. Secondly, primary treatment. Next, wastewater flows into a dual-chamber in-house tank. The upper certain chamber 24 meter cube facilitates class 2 flocculent sedimentation, while the lower upper 25 meter cube provides undisturbed anaerobic digestion.
Assalamualaikum warahmatullahi wabarakatuh to respected lecturer and everyone. My name is Nur Ain Fatihah binti Anwar and my metric number is 2023444732. Today, I'd like to present my Purpose Water Treatment Plant or WTP, which is designed to provide safe drinking water for a rural orang asli community. For this design, I selected river water as the raw water source because it is available throughout the year. However, river water contains suspended solids, organism matter, and microorganisms, so it must be treated before it is safe for consumption. This WTP is designed to serve 500 people with a maximum daily demand of 135 cubic meters per day and a design flow rate of 0.00156 cubic meters per second. Now, let me briefly explain the treatment process. The process starts with river intake, where raw water is collected from the river. The water then passes through screening, which removes large debris such as leaves, branches, and plastics to protect the downstream units. After that, flocculation is carried out by adding aluminum sulfate or alum. This chemical helps destabilize suspended particles. The water then enters the flocculation tank, where slow mixing allows the particle to combine and form larger flocks. These larger flocks are removed in the sedimentation tank through gravity settling. The remaining fine particles are then removed using a rapid sand filter, producing clearer water before the final treatment stage. The final treatment is disinfection using chlorine, which destroys harmful microorganisms and ensures the treated water is safe for consumers. Finally, the clean water is distributed to the community through a gravity-fed distribution system. For the design calculations, the calculation tank volume is 0.094 cubic meters and flocculation basin is 2.808 cubic meters and sedimentation tank is 11.232 cubic meters and rapid sand filter area is 1.20 square meters and the chlorine contact tank is 2.808 cubic meters. As you can see in the flow diagram, I selected rectangular tanks for the coagulation, flocculation, sedimentation, and disinfection units, while a rectangular rapid sand filter was proposed for the filtration process. This design is simple, economical, and suitable for a small rural water treatment plant. In conclusion, this conventional water treatment plant is simple, economical, reliable, and suitable for small rural community. It follows the multiple barrier treatment concept to ensure that the treated water complies with WHO and the Malaysian National Drinking Water Quality Standards, providing safe drinking water for the Orang Asli community. Thank you.
Good morning, Dr. Nurul Fariha. My name is Ashira. I will now present the final but most crucial part of our project, the sustainability evolution for Kampung Orang Asli Community. First, our engineering design directly support two major United Nations Sustainable Development Goals by providing safe, treated drinking water to 500 residents. We achieve SDG 6 clean water sanitation. At the same time, by treating the wastewater before it flow back into the river, we protect the aquatic ecosystem which support SDG 14 life below water. The most sustainable features of our design is decentralized wastewater treatment system or DWATS, DEWATS, because this village is in a remote forest with limited electricity. Our system operates entirely on gravity. It requires zero electricity or 0 kilowatt to run. We also choose natural biological treatment. The subsurface flow construct wetland cleans the water using natural plant and microbes, meaning there are no bad odors and no mosquitoes breeding near the village. Furthermore, our two-story in-house tank digests sludge naturally. The community only need to clear the sludge once every 2 to 3 years, making it incredible easy to maintain. Environmentally, our design is strictly compliant. The drinking water meet the Malaysian National Drinking Water Quality Standard and the wastewater meet the strict DOE Standard A before discharge. Finally, for long-term success, we, we will provide basic operational training to local villagers so they can maintain the system themselves. We have also designed the system so that solar panel can easily be added in the future. In conclusion, our passive low energy design provides a safe and sustainable solution that empower the community while protecting their natural forest environment. To conclude our group presentation, our proposed engineering design provide a complete sustainable solution for Kampung Orasli community. By implementing our conventional water treatment, we guarantee that all 500 residents will finally have access to safe, clean drinking water that meets national standard. At the same time, our zero energy, gravity driven wastewater treatment system ensure that their domestic waste is safely managed, keeping the local river clean. Ultimately, our design is highly practical, cost effective, and easy for villagers to maintain. It's not only solve in their immediate health and sanitation problem, but it's also strongly support global sustainable development goals 6 and 14. Thank you so much, Doctor, for your time and attention.